So now we're going to take a look at some different fragmentation patterns depending on the functional group. And we're going to start with fragmentation of alkanes, and we've kind of already looked at these to some extent already. And in this case, you just got to know that we're looking to form the most stable carbocations possible. We're doing fragmentation of alkenes. And so typically what we might do is to predict where you're typically going to break is just look at how substituted each of the carbons are, because the more substituted the carbocations and the radicals we form as a result of fragmentation, the more likely those fragmentations. So in this case, just label all these primary, secondary, primary, tertiary, secondary, 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 primary. And we can look and say, okay, you can cut between the most substituted carbons either here between a secondary carbon and a tertiary carbon, or here also between a secondary carbon and a tertiary carbon. So if we look at those breaks, and again here, so we can take a look at the fragments we might get here. And so in this case we might get these two fragments, and in this case you make the more substituted side the cation and the less substituted side the radical. So in here we'd have that secondary cation, a primary radical, and those are the most stable fragments we could form, so that'd be a common fragmentation pattern. Same thing if we look at the other side. So had we cut between the tertiary and secondary carbon on the other side, so in that case we would have gotten, and again this is the more substituted side, so we make him the cation, and the less substituted side the radical. That would be the most common way. It's not that it can't happen in reverse, it's just this would be the more common way it would occur. And in this case, we could look at a couple different things here. So we could look at what we have and what weight this might show up at, or what m over z technically. But we might also look at what we've lost. So we look at this bottom one here, we've lost 2 carbons. So if you kind of take a look here, we could say like a methyl group weighs 15, so that's a CH3. Whereas an ethyl group, CH3, CH2, so carbon being 12, the hydrogens each being 1, you add another 14, you get to 29. So, and then to get from the ethyl to the propyl, add another CH2, another 14, you get to 43. So, and add another 14, you get to 57, the butyl. And so the methyl, ethyl, propyl, and butyl groups. So, and technically for the propyl and butyl, these might not be straight chains, they might be branched. So, but they have weights corresponding to 15, 29, 43, and 57. So, and these are really typical. So, in this case, you're not only looking for their weights, but you're looking for their loss as well. So we look at this first one here. So the fragment on the left is 4 carbons and weighs 57. So, but you lost the radical here. Again, we only see cation, so you lost this radical, and so it also corresponds to the loss of 4 carbons, so it's also an M minus 57 peak as well. The one on the bottom here, so we've lost 2 carbons, so you might refer to this cation as the M minus an ethyl, so minus 29, and then it's 1, 2, 3, 4, 5, 6 carbons, so that's not any real special peak or anything like that, but we could calculate it out if we need to. But in this case, the big thing is that it's M minus 29, so look at what something is as well as what it's lost. So, and oftentimes one of those numbers, either 15, 29, 43, or 57 will show up and give you a clear indication of either what you have or what you've lost. Note we could have cut in some other places and had less stable fragments, but we just stuck with those most stable ones. But notice, had we cut either, let's do this in green, had we cut either here, here, or here, we could have cut off a methyl group and had like an M minus 15 peak. So, and had we cut, say, here, or one of the cuts we did, we might have had the M minus 29 peak, and we can envision an M minus 43 peak if we cut there and lose the propyl, so on and so forth. There are lots of ways for alkanes to end up with these really common fragments, or at least the loss of these really common fragments as well. So here we're going to take a look at the fragmentation of both alkenes and aromatics, because they both commonly form resonance stabilized carbocations. In the case of an alkene, they'll form an allylic carbocation, and in the case of an aromatic, they'll often form what looks like it should end up being a benzylic carbocation, but it rearranges and forms what's called the tropylium ion. We'll see that as well. So typically, we're going to knock an electron out of this molecule, and it's going to fragment, in this case, to get a resonance stabilized carbocation. So you want to identify those allylic carbons. The allylic carbons are the one, again, that are attached to the sp2 carbons of an alkene. And the idea is that if either one of those ends up as either the radical or the carbocation, it'll be stabilized by resonance with the alkene. Now, you don't want to cut in between it and its alkene, or you'd separate it from its alkene. There'd be no resonance there. You want to cut on the other side, and so this is the bond we want to cut. Notice we don't have a bond to cut on the other side of this other far allylic carbon, so it's this one we'll have to deal with. And if we cut right there, in this case, we would get a 2-carbon fragment, and then we'd get a 4-carbon fragment. So, and we want to make the more stable side, in this case, the resonance stabilized side, the cation. So, and the other side, the radical. So, and in this case, we get this resonance stabilized cation. We can draw another resonance structure. So, and there you go. We get this lovely allylic carbocation in this case. We see something similar with benzene rings. So when we've got substituted benzene rings, you want to identify the benzylic position, the carbon attached to the sp2 carbons of the ring, the benzene ring. And again, you don't want to separate it from its benzene ring, but you want to cut just on the other side. So I guess technically we're really wanting to do that here. So on the molecular ion. And when we do so, you're going to get that fragment and that fragment. We'll make the one attached to benzene, the carbocation, and we'll get this lovely radical. But that carbocation, that 7-carbon carbocation total, actually rearranges to form this carbocation right here, and it's this 7-membered ring carbocation that we refer to as the tropylium ion, and it has an M/Z ratio of 91. So these are the two common types of fragments for alkenes and aromatics. If you're an alkene, some sort of allylic stabilized carbocation. If you're an aromatic, it looks like it's going to be benzylic, but ends up rearranging to form this tropylium ion.